Okay, so today I'm going to go over what happens in a prokaryotic replication fork. Prokaryotic DNA is circular, so replication is going to begin at the origin of replication and will form one replication bubble. We eventually end up with two circular DNA molecules. So let's zoom in on this part right here. This V part is the replication fork. The two strands of DNA are anti-parallel, so they'll be going in opposite directions from each other. I'll make the top one the 5' to 3 strand, so it follows that the bottom will be going in the 3' to 5' direction. Right at the point of the fork, I'm going to put our first enzyme, which is helicase. Helicase unwinds the DNA by breaking the hydrogen bonds between nucleotides and thereby moving the replication fork in the 5' to 3' direction. As the DNA unwinds, single-strand binding proteins protect the exposed nucleotide chains from interference with replication by binding to the unwound single strand. But as the helicase unwinds these strands, it's also creating a lot of tension down the line. Like if you're going to pull on two pieces of tangled string, it just creates a lot of strain. So to relieve that strain that builds up, DNA gyrase breaks and reseals different segments of the DNA helix down the line ahead of the replication fork, removing the excess twists in the helix. DNA synthesis always happens in 5' to 3' direction, which means that this top strand of new DNA will be synthesized towards the replication fork, and the bottom has to be synthesized moving away from the fork. This means that the top strand can be synthesized continuously, making it what's called the leading strand, but the bottom strand will have interruptions in synthesis because it's moving in the opposite direction as the replication fork. So this one's what's called the lagging strand. The new short segments of DNA that are formed by this discontinuous process are called Okazaki fragments. So to start the synthesis, the enzyme RNA primase will lay down RNA nucleotides called primers so that DNA nucleotides can be attached later. These primers provide the 3' hydroxyl group that the DNA polymerases later on will need to attach the nucleotides. Next, DNA polymerase 3 does the bulk of the work of the DNA synthesis by attaching to the primer and adding new nucleotides to the 3' end of the new strand of DNA. After this is done, DNA polymerase 1 follows behind and replaces the RNA nucleotides of the primer with DNA nucleotides. So after every RNA primer has been replaced, a break exists in the new strand because the first and last nucleotides of the sugar phosphate backbone aren't bound together yet. Enzyme ligase solves this by forming a phosphodiester bond between the nucleotides and sealing the gap. So that's our diagram for prokaryotic replication fork.